This conference will now be recorded.
Hello students, we had started discussions on diffraction of light. In the last class, we had defined what is called diffraction and we had seen the conditions for occurring diffraction pattern. So just to recap, I'll just tell you what is the definition of the diffraction. Diffraction of light is a natural phenomenon where light bends around a sharp obstacle or an aperture, and as a result, light spreads into the geometrical shadow regions, and alternating dark and bright regions, just like interference, are observed. So we had seen in the last class how light gets bent at the sharp edge of an obstacle. Okay, we have seen instead of going like this, light goes like this. Okay, and for an aperture also we have seen, if you take sufficiently narrow aperture, then light, instead of going into this region alone, it actually spreads. Okay, it spreads out like this. Okay, that means, see, in this case, these regions are geometrical shadow regions. Okay, geometrically shadow should be obtained, but here what we see alternate dark bright patterns. Okay, and this is actually, this bending of light to the geometrical shadow region is called actually diffraction, and because of that we see similar pattern as we have seen in case of interference. We see similar type of patterns. Okay, diffraction pattern, but in this case the intensity of this alternate bright and dark fringes will reduce. And one more thing we'll see, that is, there will be central bright region, then this dark and bright regions will come, and the dark and bright region, alternate dark and bright regions, bright regions will, these are called actually, see, if I am okay, so let me show you. The pattern will be kind of this. If you see, there will be a broad central bright region, and then next will be minima. This is minima, then another bright will come, in between there will be dark, again another bright will come. Okay, then dark, then again bright. See, these are reducing, the intensity of these bright regions are actually getting reduced gradually. Okay, then they will become fainter and fainter, and after some time we will not see anything. On the other side also, you'll see a bright region, then dark alternatively, and then there will be another bright, then you will see some faint light. See, you will not see at all, kind of that. So you will see alternate bright and dark on either side of the central bright region. So in the diffraction pattern, I'll show you, just maybe in the second slides I'll show you how does it look like. It looks like, see, at the center there will be central bright region, and on either sides of this central bright region we'll see alternate bright and dark regions of reduced intensity gradually. Okay, all right. Now today Okay, so this is about just briefly about diffraction and diffraction pattern. If you remember, we had discussed types of diffraction also. Types of diffraction. Just this type is according to our study. Okay, according to the experimental study, types of diffraction. So we had Fresnel's diffraction, and Fraunhofer diffraction. Okay, Fraunhofer diffraction. So we are actually discussing Fraunhofer diffraction today. Okay, Fraunhofer diffraction. All right. So in Fraunhofer diffraction, what happens? Source and screen. Source and screen will be at very large distance. Okay, from infinity, actually at infinity, from the slit. Okay, from the slit. I know you are familiar with the slit word because we had already discussed Young's double slit experiment. Slit means opening. Okay, so I'll show you what is slit once again. So source to slit distance will be nearly infinite, ideally infinite, but it is very large. And the slit to screen distance also will be large. Okay, almost infinity. Okay, Fraunhofer diffraction. So this is the arrangement of Fraunhofer diffraction. So at the Fraunhofer diffraction, so we will be studying Fraunhofer diffraction, and that is actually with single slit diffraction. Okay, so what is the condition? I said in this case slit source will be at very large distance from the slit, ideally infinity, and also the screen will be at very large distance from the slit, ideally infinity. So this is the condition for Fraunhofer diffraction pattern. Diffraction. Okay, Fraunhofer diffraction. Now see, we'll see this Fraunhofer type of diffraction in single slit. Okay, so to study the single slit experiment, you know, as you are familiar now with the Young's double slit experiment, interference experiment arrangement. See, if we just replace the two slits with a single slit. Okay, see, you look this is actually Young's double slit experiment setup. Okay, see, you have a source of light. Okay, this is source of light, monochromatic source of light. Then you have two slits again. You look S2 and S1, these are actually acting as sources for interference pattern to happen. Okay, so this double slits here, if we replace with a single slit, then we'll be able to observe diffraction pattern, and that is actually single slit diffraction pattern. In this case, you look in case of Young's double slit experiment, see, secondary waves from different wavefronts are coming out and they are meeting or interfering to give rise to this pattern like maxima, minima, or alternate dark and bright regions. And in this case, we see equal intensity at all the bright fringes. Okay, but we will see different thing in case of diffraction. In single slit diffraction, let us then see just to have a correlation with this Young's double slit experiment. I just showed this experimental setup. Now let us see. This is the kind of arrangement for single slit Fraunhofer diffraction. Okay, this is actually the setup for Fraunhofer diffraction. Fraunhofer diffraction with a single slit. See what happens here. We have a single slit. This is the slit. You can see AB is the opening. This is the slit with this, say, A slit width. A. So this is the slit AB. You can see that. Now this is the source of monochromatic light. Okay. And see, as I said, in case of Fraunhofer diffraction, your source should be at infinity. So to take it at infinity, it is not possible practically. So we have to make some arrangement, right? So we had used this converging lens. You can see that L1. This converging lens, see, is kept in such a way that the source is at the focus of this converging lens, so that the rays which are coming to the slit will be parallel, and these are parallel rays, means they are coming from infinity. Okay, so parallel rays means what is the wavefront corresponding to that? Those are plane wavefronts. Okay, you see that, see, these are plane wavefronts. Okay, these plane wavefronts will come and incident at this slits. Okay, at this slit opening, you see that this plane wavefronts are actually progressing, and at certain point of time they will come here, and one plane wavefront will be at this slits. Okay, now see what happens according to Huygen's principle. Each point on the slit, or each point on the plane wavefront, will act as the source. Okay, in fact I can say secondary source, and secondary wavelets will be produced. Secondary wavelets will be produced like this. Okay, like this, from this particular point. Suppose from this particular secondary sources, this point, there will be like this. Okay, and then they will interfere. See, in this case you can see the secondary wavelets from the same wavefront, they are actually interfering to give rise to diffraction pattern. Similarly, from this point, see, wavelets will be like this, right? Like this, and they will interfere. Understand? So this interference of different secondary wavelets from the same wavefront will give rise to diffraction pattern. And see the diffraction pattern, how does that look like? It is shown here. Okay, this is the diffraction pattern, kind of like kind of interference pattern, but you look, the intensity actually varies in this case. Look why the intensity varies. I'll tell you why. So first of all, the central bright, this one is called central bright fringe. Central bright region is called central bright fringe. Okay, central bright fringe. And see, these positions are, see, of zero intensity. So these positions are called minima. Okay, minima. But what kind of minima these are? These are called secondary minima. And these, see, these are called secondary maxima. Okay, these are called secondary maxima. Okay, so these are called secondary maxima. Maxima. So similar to this is also secondary maxima. This is also secondary maxima. On either side, you can see the secondary maxima. Symmetrically, they are situated. This is a secondary minima. Secondary minima. Because see, these patterns we get due to the interference of, like, due to the interference between secondary wavelengths. That's why secondary maxima, secondary minima, and this is called central bright fringe or central maxima. This is called central maxima even. Okay, central maxima. Maxima means it will have some intensity, it will be bright points, and minima means dark point. Okay, where there will be zero intensity of light. So central bright fringe means central maxima. Maxima. So this is the kind of pattern we will get in the diffraction. But why this bright fringe having so much intensity, and why, how this bright fringe is happening here? Let us see here. See, from this, like all the points, you know, you can imagine the slit to this screen distance is very large. You know, all the rays which are coming out from the slit also are parallel. You can see that. See, these are parallel rays, right? Parallel rays. So we had used lens 2, okay, to make them meet on the screen, and the screen is actually kept at the focus of this lens 2. Okay, so the screen is kept at the focus of the lens 2, converging lens 2. So these rays are parallel rays. After refraction, they will actually meet at the focus, right? So that's why they are meeting here. That means, you know, I wanted to mean, see, I wanted to mean that this D is much greater than this slit width as well. Okay, slit width as well. Okay, much greater, much greater. That's why these rays are parallel rays. Now look, these parallel rays, see, when, see, this point O point is the central point of the screen. So this central point, when these rays, secondary wavelengths, are just going and meeting at the central point, they are all actually traveling the same path. That means there is no path difference at all. That means what? They are meeting in phase. All the rays coming all the way directly from here to the screen. Okay, all the way they are coming directly. So they are actually traveling same path, same amount of path to meet at O. Okay, so there is no path difference. So they are directly going and meeting over there. So they are meeting in phase. All of them are meeting in phase, and all the, like, all the rays, how many, see, all the rays or all the wavelengths can meet at this position in phase. So that's why it has large intensity, and it is having a broad area also. Okay, broad area. So this is central broad central region. Okay, broad central region. See here, the intensity pattern is actually drawn. I'll discuss again. Intensity pattern is drawn with angular position. So angular position of this secondary maxima, central bright fringe, secondary minima. Okay, see here, one interesting thing is that, see, the position, according to the position of this secondary maxima, they are named as first order. So this is first order, because just after the central bright fringe or central maxima, this is the first dark. This is called first dark fringe. This is the second dark. This is called second order. Second order. This is called first order dark fringe. Okay, then according to that it will go. Okay, according to the position after the bright central bright region or the central bright fringe. So this is first order minima, this is second order minima. Similarly, this is first order bright fringe or first order maxima, this is second order maxima, like that it is. Okay, so now to draw this pattern, or to know the position of the minima, secondary minima, let us first try to find out secondary minima, position of secondary minima and maxima. This is our agenda today, to find out what is the agenda, to find out the positions of secondary maxima or secondary minima. So this is very, very important, but I'll tell you this is not very straightforward. If we do the derivation part, that is actually very, very rigorous and lot of mathematical knowledge is required to do that. So we are not going to do mathematically, we'll do this. That means we will find out the position of maxima and minima or condition for maxima to occur, secondary maxima to occur or secondary minima to occur. We'll find out those conditions also by applying some tricks logically and from the knowledge of Young's double slit experiment or interference experiment. Okay, let us now go for that. So we want to find out position of secondary minima first. Let us find out minima. See here, we'll actually use the trick to divide the slit and pairing up the secondary wavelets to find out the condition when they will interfere destructively. Okay, so let us see. We'll just first take the condition itself. See, first minima will occur, suppose at P1 point. First minima will occur when path difference between the ray from, let us say this is A and this point is B. Okay, this is already given here. Let us B. When the path difference between the extreme rays, path difference between the rays coming from rays, let us say wavelets, coming from the extreme points of the slit. Slit is lambda. Okay, what I said, first minima will occur at P1, This I'm just considering here. Okay, and in fact this is the condition. We'll analytically justify why the path difference should be lambda from the extreme point. See, from here and from here the path difference has to be lambda. I think I'll just go to this figure itself. Look here. Okay, first let me tell you this condition. This is the condition, but how to justify this? So what is the path difference between these extreme points? See, the ray, let us say this is ray 1, this is ray 2, this is ray 3. All are parallel ray. Okay, all are at angle theta with the central line. You can see that. So all are bent at the same angle theta, and they are meeting at P1. Say this is P1. Say, okay. So we'll get minima, that means dark point here. At what condition? We are saying that the condition, if the ray R1 and ray R3, the path difference between R1 and R2, sorry, R3, in this case, if the path difference between R1 and R3 is lambda. Okay, so that is the condition we have here. We have to justify. Before we justify, let me find out what is the path difference between these two rays. Okay, so path difference between R1 and R3. Let us say that is delta. Okay, so we have to find out what is this delta. Let me just erase this portion. So what is this delta? Delta is actually, see, if I have to find out path difference, then see, I'm just dropping a perpendicular or normal from A to this ray R3, which is AN. So AN is actually perpendicular to this BN. Okay, so this ray R3. So we have dropped a normal AN on this ray. Okay, R3. So look, the rays from, see, the path difference between these, see, these 2 points are actually of same distance from P. Okay, in this case. So up to here, say if ray goes from here and from here, they will have the same path. Okay, they will be traveling same path. Okay, but then what is the difference? This Bn is the difference. So Bn is the path difference here. Okay, Bn is the delta path difference. But what is Bn? We have to calculate this Bn in terms of screen to slit distance, d, capital D, or lambda, the light used, or the slit width. In terms of this, we have to find out what is this delta. So to find out this delta, let me tell you, see, if this AN is perpendicular to this ray, since this ray is parallel, so this total angle also will be 90 degree. If you agree with me, then I'm happy. Okay, so then you have understood this. So this is perpendicular 90 degree, right? So this much is theta. So how much is this part? So I'll just show you one by one. So this much angle is 90 degree. This is theta, right? So how much will be this? This is 90 minus theta, right? Again see, this line, this particular line is perpendicular to this AB, isn't it? This particular line this is perpendicular to AB. You look here, perpendicular to AB. Now if this is 90 minus theta, I have to make this whole angle 90 degree, then this must be theta, because look, this angle is 90 minus theta, this particular angle is 90 minus theta, so I have to make this whole thing 90 degree, so this must be theta. Okay, so I hope you have understood what is this angle BAN. So BAN is angle theta, right? This is angle theta, as you can see denoted here. Now I have to find out what is BN. So this is actually, see, this is a right angle triangle ABN, right angle triangle, isn't it? Right angle triangle. So from here, what we can write? From this right angle triangle, what we can write? We can write, see, BN perpendicular by hypotenuse is this one, AB. BN by AB is sine theta, because the angle will be always between this AN is actually, say, this is base, AB is hypotenuse, and BN is actually perpendicular. Okay, so AB we have taken as a slit width. AB is slit width. Okay, so we know AB is a slit width we have taken. So this will be AB sine theta. BN is equal to AB sine theta, which is A sine theta. So what is the path difference between these rays R1 and R3? The path difference is A sine theta. And what is the condition we have got, or we have considered to have dark fringe at this point P? This A sine theta must be equal to lambda. This is the condition. Okay, this is the assumption we have made. Now let us justify this. Okay, so we have got A sine theta is equal to, sorry, A sine theta is equal to lambda. Okay, if theta is very, very small, then we can actually write A theta is equal to lambda. So those things will come up later. Let me justify why this P1 will be dark if this is satisfied. That means if the ray, see, if I just take the ray R3 here, this R3 and R1, if the path difference between them is how much? Lambda, then it will be dark fringe. How? To justify that, let us divide this whole slit AB into two parts. Let me tell you, okay, let me name this middle point of the slit to be M. Okay, middle point is M, say. Okay, now see, one ray goes from A, another ray goes from M. What will be the path difference between them? See, if the path difference is A, now the slit width, see, between A and M, slit width is A by 2. If I put it here, A by 2 sine theta is equal to lambda by lambda. Then A sine theta is lambda by 2. Okay, that means what I'm trying to say, see, this must be lambda by 2, right? I'll clear you again. See, if the path difference between the whole, like path difference due to the whole slit is lambda, then when I make two halves, so ray from the top most point and middle point, they will have path difference lambda by 2. Okay, so this can be easily proved. See, if I have a triangle like this, okay, and if the path difference, if this path difference from these two rays, okay, lambda, then see, if I take this middle point, see this triangle, if this is a b n, and now this is a m, let us say this is n prime. So these are actually similar triangle, isn't it? Okay, similar triangle, isn't it? So the ratio of the sides will be the same. To keep it same, the path difference has to be lambda by 2 for these two rays. Okay, the path difference between these two rays has to be lambda by 2. You can see that. Or I can tell you very simple language, if the path difference for the whole slit, okay, or if a corresponds to lambda, then a by 2 must be corresponds to lambda by 2. If slit width corresponds to slit width a corresponds to lambda path difference, then slit width a by 2 must be corresponding to lambda by 2. If I have divided into 3 equal parts, then this a by 3 corresponding to lambda by 3 by 2 into lambda. Okay, this must be like this, isn't it? All right, so let us now see how this p point is going to be a dark point. See, if I divide the whole slit into 2 equal half, okay, then see the ray from here and from here, from a point and m point, where the slit width is a by 2, will have path difference lambda by 2 between them. But what about, see, just this point, say this point, okay, just below this top point, if I take a point like this and just corresponding point in the below half, okay, this is the upper half and this is the lower half. If I take the corresponding point in the lower half also, then how about the path difference between these two rays or these two waves? This also will be lambda by 2. I can give you simple numbers so that it will be easier for you to understand. Suppose I have some 10, suppose I have slit width between this, I have slit width 10. That means I can just make 10 dots like this, 1 2 3 4 5. Let me take one more here. So this is 1 2 3 4 5 6 7 8 9 10. Okay, so like that. So if I make it half, so upper half there will be 5 points and here there will be 5 points, okay, in the lower half. Now if for the 10 slits or 10 points path difference is lambda, then from 1 to, see, 1 to 6, or this I can say 0, this 0 to 5 will have path difference lambda by 2. Now if I take first one, then I have to go to sixth one, corresponding sixth one. So sixth one and this first one will have path difference lambda by 2. Okay, so 1 corresponding to 6 will have path difference lambda by 2. 0 corresponding to 5 will have path difference lambda by 2. Okay, then you will have 2 here, 2, you'll have 7 here. So between 2 and 7, there will be path difference lambda by 2. Like that, whatever source you take from here, whatever point you take from here, there will be a corresponding point in the lower half also. So if you take any point in the upper half, there will be a corresponding point in the lower half for which the path difference will actually become lambda by 2. And why I'm saying lambda by 2? And if this is lambda by 2, what happens? What happens when there is lambda by 2 path difference between two waves? Let me tell you. See, if I have discussed interference in the beginning itself. If I have wave like this, okay, so if the other wave also have, we have like this, that means, you know, if the crest and troughs are occurring at the same point, then they are interfering in phase, or they are in phase. But if suppose the path difference is lambda by 2, that means pi, lambda by 2 corresponds to pi, or 180-degree phase difference. That means, you know, this is like this. So if it is like this, so where tau is happening here, we have, sorry, here crest is happening for the wave 1, and here for wave 2 the crest. So if we just have same, suppose 5 amplitude 5 here minus 5, if you add them, what will be the amplitude of the resultant wave? You will see 0 intensity or 0 amplitude. Okay, so this is all what will happen when the path difference is lambda by 2. Okay, so see, zeroth source corresponding to fifth source, they will see the wavelet from zeroth source and fifth source, they will interfere destructively, giving rise to 0 intensity. Then the first source will interfere destructively with the wave from the sixth source. Similarly, from the second source, the wave from the second source will interfere destructively with the wave from the seventh source. Like that, you will have all corresponding points in the upper half. Okay, you will have, if you take one point in the upper half, you will get a corresponding point in the lower half, for which the path difference will be lambda by 2. That means those waves will interfere destructively. Okay, and that's how ultimately no ray will, like no two waves will be available to interfere constructively to give you some intensity in the at this point. So this is how, see, you will get dark point over here, or minima. Dark point means 0 intensity, that means minima. So totally destructive interference will occur at this position. So what is the condition for that? So this is the for first minima, this is for first minima or first order minima. What is the condition? A sin theta is equal to lambda. This is the condition for first minima to occur at P1 point. Now I think you will be interested to find out the position for the next orders, right? Next other minima also. So to do that, suppose I want to see the second order minima. So condition for that will be A sin theta, this path difference must be 2 lambda. Okay, this path difference must be 2 lambda. Okay, let me explain you how. See, to explain that, you have to Suppose you have 2 lambda path difference between the rays. See from the extreme point, like see here. Now from the, see if I say this is ray 1, R1, this is R2 and R3. So in this case, path difference between R1 between R1 and R2 must be 2 lambda, must be equal to 2 lambda to have second order secondary minima at P1, or here P, okay, at P. See path difference, you know that this is a sine theta alone. So a sine theta will be 2 lambda. So to explain at at this condition, why at this condition this point will be dark, second order dark. Let us explain that with this. So in this case, if we want to have CP2 point, second minima, position for second minima, I have to divide the slit of width A into 4 equal part. Okay, 4 equal part, and each of them will have width A by 4, A by 4, A by 4, A by 4. So you have A by 4. Excuse me. So in this case, see what will happen. The point, see this, if I say this is the top point in the first half, so point in the first half, and the extreme point in the second, in that half itself will actually will have, see this R1 and R2 will have path difference lambda by 2. Okay, lambda by 2 path difference, they will have path difference lambda by 2. Similarly R3 and R4 will have path difference lambda by 2. Excuse me. So if you take any point in the first half, then there will be corresponding point in the second half to cancel out. Okay, similarly if you take any point in the second half, there will be a point. Okay, if you take in the any point in the third half, you will have a point, corresponding point in the fourth half. Like that, you will have each point will have its corresponding point in the other half to find out, like to cancel out the effect of that. Okay, so that you get destructive interference. So like that, if you want to have the higher orders again, suppose I want to have third one, then you have to divide this into 8th half. Okay, 8th half, having each of them have this. Okay, so like that, if we divide equal number of halves, the slits, if we divide equal number of half, okay, so first half will have a point, and corresponding to that point there will be another point in the second half to cancel. Okay, if you take any point in the second half, you will have a point, corresponding point in the third half. Like that, all the points will have their corresponding point to cancel out. Okay, so this is how you'll get and eventually we'll see the condition will be satisfied. A sin theta is equal to 2 lambda. Like that, if we want to go for the third secondary minima, then the condition will be A sin theta is equal to 3 lambda. Like that it will come. So if we want to generalize this for n dark fringe or nth secondary minima to occur, condition for nth secondary minima what is the condition? Condition is that A sin theta path difference must be equal to n lambda. Okay, this is theta n, suppose n. Okay, so n can be 1 2, it cannot be 0. Okay, n can be 1 2 3, okay, like that. Okay, any order you take. So what is the condition for secondary minima to occur? That is A sin theta is equal to n lambda. All right, so you can actually get easily from this, like position for the minima. Okay, now let me tell you here itself. See this position from the center point, say this is y1 or yn, say see y, let us say y1 for the first order minima. So this is the linear position. Okay, this y1 or y is linear position from the central maxima. Okay, linear position from the position. So how to find out that? See, we get the condition A sin theta is equal to n lambda. Okay, look from this here geometry. See, I have this ray. Let us take this ray up to here, and then like this. So you take this triangle and try to write. See, this is A sin theta is perpendicular. This is y by I'm sorry, this sin theta for small angle, I can write this as tan theta also. Sin theta can be written as tan theta for small angle. Okay, I will write that for small theta. Okay, now you can just write it. So this is y by d. D is the base. Okay, perpendicular by base. This is equal to n lambda. So from here, actually, you will find the position of this. This is y1. So okay, so let us say this is lambda. Okay, for the first one, y1 is obtained as d lambda by a. This is the linear position of the first one. So similarly, you can generalize. So yn, the position from the nth position, linear position from the central maxima. Okay, this is position. Okay, I'll write it here. This is a linear position. This is a yn. If we generalize, we will have n lambda into d by a. Okay, this is the general one. Okay. All right. So what will be the angular position? Angular position will be theta, right? This theta you have to find out. So if this, see from here itself, we can find out angular position. let me write it here. If theta is small, then we can write this a sine theta. So angular position of angular position of secondary minimum. That is, see from this condition, a sine theta is equal to n lambda. So I am just going for the general formula. So this, if this angle is theta, theta is very very small, then I can write this nearly sine theta nearly equal to theta, right? So I can write from here. So theta n. So this is theta n. Theta n will be L lambda by a. So this is the angular position. All right. Let us now see how to find out the position for like bright position for the secondary maxima. So okay, so position, let us say position for first maxima. Secondary. Obviously I have to actually refer to this, I'm sorry, this figure itself. Let me just take this figure. So to have secondary, first order secondary maxima, you know the condition is, see path difference, this is this n sine theta has to be 3 lambda by 2. 3 lambda by 2. You might be thinking how I am writing. Yeah, we are writing fast because this is not very trivial calculations to show you this condition. You learn this in the higher classes, maybe in the graduation. So this is this is the first. So this path difference Bn has to be 3 lambda by 2. So to analyze that, let me just divide the slates. Okay, divide the slates into 3 equal parts. Okay, like this. So this is first part, second part, third part. What we have seen, see for the extreme 2 part, if this is lambda, 3 lambda by 2, path difference between these two rays, this is R1, this is R3, and this is R2. So path difference between R1 and R3 has to be 3 lambda by 2. If I divide them equal half, like this is A by 3, this is A by 3, this is A by 3. So you look, the path difference for this will be lambda by 2. For this much it will be lambda by 2. For this much also it will be lambda by 2 path difference, right? That means any ray you take from here and here, they will actually interfere destructively. If you take any rays from here between these two, they will interfere destructively, isn't it? All right, now look, you can look one thing. If you take any ray from this position and this position, what is the path difference between them? This will be actually lambda. So this is actually giving you constructive interference. If you see See the path difference in interference, you have seen, right? Path difference lambda. Lambda is corresponding to 2 pi phase difference, right? So lambda path difference corresponding to phase difference 2 pi. That means they are meeting in phase. So if you divide your slit into odd number of halves, see, suppose I divide into 3, 1, 2, and 3 halves. See these two guys, okay, any points you take from these two guys or between these two guys, they will interfere destructively, but the rest of the portion will be empty. See, there will be no rays or no wave remaining to interfere destructively. That means the whole ray, see, now I'll explain once again from here. See, any ray you take from this point and this point, so they will destructively interfere. Okay, that means that point will happen. You take any point from here and corresponding point from here, they will actually interfere destructively. Anyway, similarly, you take any point from here, any point from here, corresponding point, they will interfere destructively. Okay, so they will all interfere destructively. But what about this portion? Okay, there is no conjugate point kind of that. Okay, to destructively interfere from, like with the wavelets coming from this particular portion. Okay, so 2a/3 this position, okay, any point you take within this, they will take any point you take within this, there will be corresponding point to destructively interfere. Okay, but this remaining a/3 portion, this portion will not have any conjugate wavelets, okay, to interfere destructively. So all the rays or wavelets directly they will go and interfere that particular point. Okay, but you know, since this portion is very small or very narrow portion, limited amount of light will go and meet that position. Okay, that's why intensity will be less intensity compared to the central bright range. Okay, similarly, if we want to have the second order secondary maxima, then what you have to do, you have to have your condition for the secondary maxima, for second order secondary maxima. What is the condition? The path difference between this R1 and ray R2 has to be a sin theta is equal to 5 lambda by 2. And you have to divide, to understand this, you have to divide your slit into equal 5 part. Okay, 1, 2, 3, 4, another part 5. And see, this has slit with a/5, 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 a/5. Okay, up to this, if you take any point, there will be a corresponding point which will be destructively interfere. But this particular portion, this a/5 portion, this portion will not have any corresponding points to send waves to interfere destructively. So light through this particular position or this particular portion will directly go and meet that position. Okay, position that will go directly to the position where the second order secondary maxima is occurring. Okay, so you will get further lesser intensity, because earlier we had light from a/3 portion of the opening, okay, of the slit. Now you are getting light from a/5 portion of the if this is suppose some 10, now you get, if this is 10, earlier you are getting from 3% or 33%. Now you are getting, you know, 20. Yes, so maybe 20%. Okay, 20%. Okay, 20% of the slit will actually contribute to the light, contribute to the this secondary maxima, second order secondary maxima. Like that, you know, you have to divide into odd number. If you want to see the third order, you have to divide into 7 equal part, and the condition has to be 7 lambda by 2. So in general, the condition for condition for nth order secondary maxima secondary maxima is given by a sin theta is equal to 2n plus 1 lambda by 2, where n starts from 1, 2, 3, like that it goes. So n is equal to 1 means first order secondary maxima, so it will be 1 means 3 by 2, right? 3 lambda by 2. Okay, so this is actually the condition. Now let me okay, I think this figure is not required. I'll just erase this, and here I'll show you few more things here. For the secondary maxima, once we get the condition, general condition, let me find out the position. Okay, linear position. Linear position of the secondary maxima. I'll go with the general condition or general one. So this part again, it will be, you know, y by yn by d. So 2n plus 1 lambda by 2. So yn will be 2n plus 1 d lambda by 2a. Okay, this is the position. And what will be the angular position? See, from here itself we can find out. A will make this as theta. Okay, we'll make this as theta. So you'll get 2n plus 1 lambda by 2. That means, you know, theta will be 2n plus 1 whole into lambda by 2a. Okay, this will be angular position. So I'll just directly write this. These are required because you will be asked in course, numerical problems will come from this particular things. Positions of secondary maxima. Okay, so that is theta is equal to 2n plus 1 lambda by 2a. Okay, so this is the one. Look, just to remember a trick, just remember trick. So what is the relation between this linear? If you know, if you remember only one, other one can be remembered. Okay, just this d is the only one which is not there here, isn't it? Other things are all equal. That means, you know, linear width if you know the angular width into d, this will give you linear width. Okay, this is theta n, say. not with linear position. So y1, yn is equal to d into theta n. You can remember in this way. That means just d you have to multiply with the angular width so that you get linear, sorry, not angular width, this is the angular position. Okay, just to go get the angular linear position or vice versa. Okay, so this is the relation between yn and theta n. Okay, now we'll find out what is, see, we can now write the angular positions, right? This, if I say 0 or o 0, say this will be, what will be the first linear position for the minima? See here, I have positions here. So this is angular position, okay, lambda by a. If it is angular position, so angular position, this will be lambda by a, this side lambda by a, and this side it will be minus lambda by a. Okay, so this will be 2 lambda by a. Okay, this will be 3 lambda by a. This will be minus 2 lambda by a symmetrically, and this minima will be minus 3 lambda by a. Right? These are the angular positions of the minima. We have written already how to get it. Now, if you want to find out right position of this, then what will be this? So 2n plus 1. See the linear position. So this is angular position. So for the first one, it will be 3 lambda by 2a. Right? This will be 3 lambda by 2a. 3 lambda by 2a. That means 1.5 lambda by a. Okay, this is 1.5 lambda by, this is 5 lambda by 2a, 2.5. Okay, like that. In this side minus, this side it will be plus 3 by 2 into lambda. This will be 5 by 2 into lambda. Okay, these are the positions. Okay, angular positions. Now, what is the angular width of this central maxima? What is the angular width? Angular width central maxima. See, if you know like this, you can find out, see, that this is the angular width, right? That means 2 lambda by a, isn't it? This is very simple from here. But see, from here also we can do this. Suppose this is the first minima. This side also, this is first minima. Okay. So the central maxima actually situated between first maxima. So what is the angular width? See, this is 2 theta. 2 theta. Angular width is 2 theta, isn't it? 2 theta. So this 2 theta, yeah, so this is actually 2 theta. What will be linear width then? So what? Okay, so 2 theta means what? Theta means what for minima? Angular position. Look here. Theta is n lambda by a. For the first one, lambda by a. So theta 2 into lambda by a. So this is how you can find out the angular width. What is linear width? Linear width is actually beta. See, I can just take this triangle, isn't it? I can write tan theta. Tan theta, beta is equal to tan theta, 2 tan theta, okay? Because up to this, 2 into tan theta. So 2 into tan theta means what? If this is y, see this is the y1, see y1. So y1 divided by d. So what is y1? y1 by d, right? So what is y1? we had got A into y1 by d is equal to lambda. So y1 was actually lambda d by a. Let us put it here, lambda d by a. So it is actually 2 lambda by a. Let me check. No, I'm sorry, this is actually linear, this is angular itself. Okay, this is angular with this cell. Okay, let me tell you. Okay, so we can actually find out. Okay, so let me find out width of the central maxima. Central maxima. So how to find out that? See, if you want to find out that, so this is y. See, we know linear width. Okay, for the nth one. Okay, if I just say beta can be written, just let me write it and then see whether you can. So this is for the dark one. Okay, I think I was correct only. So yeah, so I think it is 2 into lambda 1 y1 itself. Okay, so y1 is d lambda by a, d lambda by a, right? So d lambda by a, so it is actually, yes, so this is the actually width 2 into y1, because this much is y1 and here also this much is y1, 2 into y1. So y1 we know d lambda by a, right? So this is the condition we have written already. Position of see, this is for d lambda by, so y1 means d lambda by a. So this into 2, that will give you the linear width or fringe width of the central maxima. Okay, now if we want to find out fringe width of this central maxima, this width of the central maxima, sorry, secondary maxima, width of secondary maxima, width of secondary minima. I'll just finish with this, writing secondary width of secondary maxima and width of secondary minima. Secondary maxima, let us write secondary maxima first. So width of this means, you know, you have, see here, this is the first minima. It is actually, see, secondary first order, or any I can actually write any order of that. Okay, any order. See, I just want to show you with the first bright or first secondary maxima. See, this is actually in between first dark and second dark. Okay, so if I write, see, secondary maxima, this will be written as y1 yn plus 1 minus yn. This is for dark or minima. Okay, this is for minima or dark. We have already found out this is, see, it will be n plus 1 d lambda by a, and here it is n d lambda by a. See what happens, this will be d lambda by a. Okay, d lambda by a, isn't it? So this beta is actually, beta secondary maxima will be for, this is for secondary maxima, beta secondary maxima sm. Okay, sm is d lambda by a. All right, for minima what will happen? See, for if I just want to get for minima, so this is the position for this and this, so in between there will be minima. Okay, in between there will be minima, right? So I can get width of secondary minima, secondary max, and this is minima, mean, beta for that. See, for that, you need to have positions, say position y n, suppose n bright, okay, bright minus yn minus 1 bright. Okay, if you write this, the condition was, the y1 for bright was 2n plus 1 into d lambda by 2a, right? This was the condition. Now y1 minus 1 will be 2n minus 1 plus 1, this whole into this, d lambda by 2a. So now take the difference of this, say 2n minus 2, that means minus 1 will come here. So y1 minus yn minus 1 will give you 2n will cancel each other. This, there will be minus 1 here, so this will be actually making it plus d lambda by 2a again. So it is actually d lambda by 2a. Okay. So position for the width of the dark fringes will be, okay, so just a minute, I think there will be 1 here, so this will be 2 d lambda, okay, this difference, so ultimately d lambda by a. So this also will be actually d lambda by a. Okay, d lambda by a. So width of this secondary maxima and secondary minima will be the same, that is d lambda by a, d lambda by a, d lambda by a. And what will be the width of the central? The double of that. Okay, double of that, that is 2 d lambda by a. Okay, for the bright one. Okay, 2 d lambda by a. And angular width also will be twice of this actually. Okay, this will be theta, and this will be 2 theta. All right, so we'll see in the next class, we'll see the intensity ratio. Okay, intensity ratio, like how intensities are here in the central bright and in the minima. Okay, so how that varies, we'll see in the next class. So thank you for your patience. Bye for today.